Hello, good morning class. Right, so who still didn't join the class? Uh, Avinash only. So only Avinash didn't join, okay? Alright. So yesterday I think we already finished until here, right? Can someone please check for me? Alright, set 3.2, okay. I can close this one. Alright, so today we finish, right? We finish for Kepler's law. Okay, before I continue, right? So on Tuesday, okay, on Tuesday we will have a class, right? A tutorial, I think. Oh, no. I mean next Monday, yeah. So next Monday, we have a tutorial class at 7:30 until 8:30, right? So I will do online quiz, right? So I will give you a link, okay? So I will join you at the same time using the quizzes. So online quiz for chapter 1, 2, and 3, okay? So please be prepared, right? So maybe like 40 questions, okay? Objective and maybe some objective, some subjective. Saturday class as usual at 2 until 3. Okay. I will give you an exercise because I think we only have like two or three more questions that we still didn't discuss, right? So I will give you some other question because I think it's not enough with 1 hour. Okay, so I will give you later for that one. And on Monday, please be prepared for the online quiz. I will give you the Google Meet link. Okay, and also the same time the quizzes. Okay, so make sure you prepare. So that one I will put as your PBD for chapter 2 and chapter 3. Okay. So let's continue for 3.2. So Kepler's law. So there are three Kepler's law. First one, the second one. The first one is the law of orbit. Second one is the law of area. Okay, and the third one is the law of period. Okay, so there are three Kepler's law. Okay, so the first one is let's see. Okay, who is the Kepler is actually. Okay, so actually in Form 3, right, you already learned about the law of orbit, right? I think on chapter 10 or chapter 11, if you remember. Okay, where you already know that actually our orbit, okay, our orbit is actually in the ellipse, okay, in the ellipse shape, okay. So this is the guy, right? This is the guy that actually discovered the Kepler's law. Okay, so the name is Johannes Kepler. So it's a German astronomist, okay, a mathematician and also astrologist who formulated three laws that describe the movement of the planet around the sun. So the first Kepler law, Kepler's law is the all planets move in elliptical orbit with the sun at one focus. Okay, so mean the sun is the center. Okay, and the planet is revolute, right, around the sun. So this is called as the law of orbit. Okay, so this is the animation, okay, to show that actually how does the planet, okay, rotate around the sun. Okay, so you can see it's in an ellipse form. Alright, so this is the activity, right, to show, right, that actually that the our orbit is in ellipse shape. Okay, so there are two. So for the first one, you have to draw the n axis. Okay, two axes. Okay, the major axis. Okay, so this is the major axis, right, and this is the minor axis. Okay, and you put the two thumbtack here. Okay, on the paper. Okay, so this is actually represent the sun. Okay, so this is actually represent the sun, and this is actually represent the planet. Okay, So and then you tie the thread, okay, at the thumbtack and also at the pencil and also to the another thumbtack here. Okay, so later I will show you, okay, a video, right? So how actually you want to draw this one. Okay, okay, so this the right. So this is two thumbtack. Okay, so this represent the sun. This is represent the planet. Okay, and the thread is actually being tied already with the pen and also with the these two thumbtack. Okay, so this is the axis, the major axis and the minor axis. Okay, so starting from the major axis on the left, right? So you just underline it until here. Okay, and then after that, okay, you go back, okay, at the upper part here and you underline it here. So you form the ellipse shape. Okay, so this is actually represent, right, our orbital shape. Okay, so let's see again. You can do this at home. Right, so you form the ellipse shape. Okay, and so based on the activity just now, right, so name the shape of bits used by the planets in the solar system. So you call it as the ellipse. Okay, so describe how the distance between the earth and the sun changes when the earth makes a complete orbit around the sun. Okay, so the distance is further at the major axis. Okay, so you can see here at the major axis, the distance is much further. Okay, if you compare, right? So the distance is much further. Okay, and then the next one, right? Discuss how the shape of the Earth's orbit, okay, will be if the major axis is almost as long as the minor. So means the major axis is the same length as the minor. So how does the shape? Okay, so the shape will like almost round. Okay, the shape is almost round. Okay, so this so what we can conclude here, right? So the planet in the solar system have elliptical shape orbit, okay, and the sun always stays on the focus of the ellipse, or we can say it that the sun is like a center, okay, of the ellipse, okay. Alright, and then the major axis is longer than the minor axis. So you can see here from here to here, the major axis is longer than the minor axis. So if you draw and you try to measure the major axis from here to here, you will see that the major axis is actually longer than the minor axis. Okay, as such, the shape of the elliptical orbit of the planet in the solar is almost round. Okay, it's almost round, and the planet can be assumed to make a circular motion around the sun. So even it's an ellipse shape, okay, but we can assume that it's almost like in a circular shape. So we can say that it's actually moved in a circular motion, right? So the radius of the orbit is the average value of the distance between the planet and the sun. So the radius of the orbit is the average value of the distance between the planet and the sun. So let's say this is the sun, this is the planet. So this is actually the average value of the distance. Okay, so this is the radius of orbit. Right. Okay, so that is the first Kepler's law. So it's actually for the first Kepler's law, it's actually just describe the shape of the orbit. So you have to know that it's actually in ellipse shape. Okay, and for the focus, okay, the focus of the ellipse is on the sun. Okay, so that is the first Kepler's law. Okay, now we move on to the second one. That is a Kepler's second law that we call it as a line that connect a planet to the sun sweeps out equal area in equal time. So this is called as a law of areas. Okay, law of areas. Okay, so this is the diagram. So what does it mean here? Okay, so let's say there are the area here. Okay, the area of, okay, CFD, okay, is actually same as the area of BFA. Okay, so it's actually same. So this is the area of the CFD, and this is actually the area of BFA. Okay, so actually the area is same. Okay, as long the time is same. Okay, means the period is same, right? So the area is same as long the time or the period is same. Okay, and how about the velocity here? Okay, so we already know that v is actually equals to s over t, right? So as you can see here, the length of BA, right? The length of BA is actually higher than the length of BC. Sorry, CD. Okay, CD. Okay, the length of BA is actually higher than the area of CD. Okay, so when the length is here is higher, the length is higher here, so means the the distance is higher. So when the distance is higher, the speed is also higher. So mean here the speed is higher if we compare to the CD. So this one the speed is lower. Okay, because of the distance here. So the distance traveled by BA is higher than CD. So when the distance higher, the speed is also higher. Remember, we have to use the speed. We cannot use the velocity, because you know when they rotate, right? When they rotate the sun, the direction is always changing, right? So we cannot say that the velocity is same. We only can say the speed is same. Because if you say the velocity is same, means they move in the same direction. But as we know, when it rotates, right, it keep changing the direction. So we cannot say the velocity is same. We just say that the speed is same. Okay. So here, right? So here you can see the speed is higher at BA, and this one the speed is lower at CD. Okay, because due of the length of the travel. Okay, the length of the each point. Okay, it says CD and BA. Okay, so if planets take the same amount time to move from A to B and from C to D, okay, the area of AFB is same as the area of CFD. So this one already explained. Okay, the area is same if the time, okay, is same. Okay, it's the time for from B goes to A is, let's say this is 24 hours, right? So this one is also 24 hours. Then we can say that both area is same. Okay, distance AB is longer than distance CD. Okay, so I already tell you this one. So the planet is moving at a higher linear speed from A to B than C to D. Okay, so this one also I already tell you why, because of the distance travel is higher. So means the velocity, the speed is also higher. Okay, so you can see here from the animation, you can see when you move, right? So when you enter at this part, you can see it move faster, right? And then when it goes back here, it moves slower. Okay, so it moves slower. Okay, and then when it moves this part, you can see it moves faster. Okay, so that's proof that actually um, the speed, okay, at the speed at this part, okay, is higher than on this part. Okay, that is the Kepler's second law. So we move on to the Kepler's third law. Okay, so actually Kepler's third law, this one is involving the derivation of the formula. Okay, so the square of the orbital period, okay, the square of the orbital period, okay, of any planet, okay, so it doesn't matter whether it's Earth, Jupiter, Mars, okay, Neptune, okay. So the t square is actually directly proportional to the cube of the radius of its orbit. So this is called as the law of period. Okay, t square directly proportional to r cube. This is called as a law of period. So remember the first one is law of orbit, right? Law of orbit, where it said that orbit is actually in ellipse shapes, right? Okay. While sun is at focus, right? And the second one we learn about law of area. Okay, law of area. Okay, so the area of let's say just now PFA is actually equals to area of CBD, right? Example, as long as long the time is same. Okay, so the third one is this one. T square is directly proportional to R cube. So this is called as a law of period. Okay. So this is for this picture, this diagram. It shows like how much time, okay, how much time the one planet, right, needs to make a one full rotation. So let's say if I take Mercury, right? So Mercury is only need like 0.2 years, right, to make a full complete one rotation, okay, around the sun. Okay, while let's say for the Mars, it take like 1.9 years. So actually this the year is actually according to the Earth. Like 1 year is 365 days, right? So if like Mars 1.9 years means you have to multiply 1.9 times 365. So that's how long that the Mars need to make a one full complete rotation, okay, around the Earth, around the Sun. Okay. So a planet which orbit with a larger radius has a longer orbital period. Okay, so means the larger the radius, the longer the time need to make one full rotation. So here you can see the Neptune, right? The Neptune that it needs like 164.8 years, right, to make one full rotation around the sun. Okay, that's very long. Okay, and the planet which are further from the sun take a longer time to complete one orbit around the sun. So, if it's further than the sun, means the time must be longer. Okay, to make a one complete full rotation. Okay, so for example, the Earth take 1 year to make one complete orbit, while Saturn takes 29.5 years. Okay, to make one full complete rotation. Okay, so you can see here, right, when if the radius is lower, right, okay, you can see it's very fast to make one full rotation, but this one, okay, take longer, okay, compare with the one that closer to the sun. Okay, and this is actually the equation for the Kepler's third law, right? T square is directly proportional to R cube. Okay. Before I move on, okay, so any question you want to ask about first Kepler's law, second and third? Are you clear? Right. If you have anything to ask, you can just ask, right? Okay, so this one you already see the diagram, right? How long does the Mercury needs to make one full rotation around the sun? Okay, so this is the orbital period. You don't need to remember this one. Okay, so this is the part we have to formulate the Kepler third law. Okay, we know that T square, the period, the T square is directly proportional to the R cube, right? The period of the square period of the time, okay, for the planet to make one complete circle, okay, around the sun is actually directly proportional to the cube of the radius of the planet. Okay, so the Newton's law can be formulated, okay, using the Newton's law of gravitation and concept of circular motion. So planet make circular motion around the sun. Yes, we know that actually is our orbital shape is an ellipse, right? But we can say that actually our is move like in a circular motion, almost a circular motion. So we can use the circular motion, circular formula. Let's say if you want to calculate the circumference, we can use the circle circumference formula to calculate it, right? So the first one, okay, the centripetal force is actually equals to the gravitational force between the sun and the planet. So this one we already learned in 3.1, right? So I already told you, let's say there is a planet here. Let's say this is the Earth. Okay, this is the Earth and this is the planet. Okay, so there must be a force between both these like Earth and a planet. No, a satellite. Sorry. So there must be a gravitational force between them, right? Between the Earth and the satellite between and Earth. Okay, so this gravitational this gravitational force, okay, is actually equals to the centripetal force also. Okay, so it actually is equal to the centripetal force. So this one you have to know. So let's say if there is sun, okay, and the sun, they say this is sun and this is the planet. Okay, this is the sun. Where's mine? Yeah. So this is the sun and this is the planet. So there must be a gravitational force acting on both of it. Okay, so the gravitational force is actually equals to the centripetal force. So that's why we got this equation, right? Okay, so how you want to derive, okay, the relationship between the orbital period and the radius, because we know the Kepler's law is actually involving the period, okay, the period and also the radius. Okay, so how you want to derive, how you want to make a relationship between these two variables. Okay, so here from here mv square is equals to mv square r is equals to gmm over r square. So this one I already explained. We assume that actually the gravitational force that acting between the planet and the sun is actually equals to the centripetal force. So mv square r is equals to gmm over r square. Okay, so from that, okay, we start to derive r square. So I just cross multiply, okay, mv square r square equals to g m m times r, right? Okay, so this m I can cancel this one, okay, and this r I can cancel this one, so this one will be like only one r left. So it will be left like v square r equals to gm, okay, and v square is equals to gm over r. Okay, so I got like this. Okay, and from 3.1 also we already learned how to derive the velocity. So the first part you already know v is equals to s over t. Okay, so what is the s? S is the distance, right? So the distance the distance that how far? Okay, how far does the planet we travel to make one full circle, one full rotation here? So what is the distance? So this s is actually because I already told you it move in the circular motion. So we can use the circle formula, okay, the circumference at 2 pi r, right? So 2 pi r. So the distance is 2 pi r. Okay, and the time here is actually the period. Okay, how long does it take for the planet, okay, to move in one complete circle? So should be the period t. So this is the value of v. So I just substitute this one, this v, into v square here. So should be 2 pi r over t. Okay, so this one have to square it. So it will be like this. Okay, then I just square pi square r square, right? And then over t. Okay, So it equals to Gm over R. Okay, and then again I cross multiply it. Okay, so 4 pi square R square times R equals to GMT. Okay, just cross multiply it. Okay, and then this one I will get 4 pi square R cube. Okay, GMT. Okay, so if I want the, sorry, this one also have to be T square. Okay, because this one I square all of it, right? So this one also have to be T square. Okay, so T square. Okay, and then after that, the T square is actually equals to, okay, this one is multiply, right? So when it goes here, it will become divide. So 4 pi square R cube equals to GM. Okay, so from that, you know that pi is a constant value, right? It's the value is always same, right? 3.1.42, or you can use to 22 over 7. Okay, and while the G is the constant for the gravitational flight, 6.67 times 10 power of negative 11. So it will not change. Okay, and the mass of the earth also constant, right? That is 5.97 times 10 power of 24. So all these, the one that I make a circle, okay, this one. So all inside the circle that I made, all the value inside of the circle I made is actually a constant. So I can just replace this one with the value of K. So K is the constant. So when I replace with all the value here with K, so it will become T square KR cube. While K is actually this one, 5 pi square over GM. Okay, so you will get like this. So this one we call it as a Kepler third law. Okay, Kepler third law. Okay, so do you understand how do I derive? So I explained step by step already. Or do you want need me? Do you need me to explain again? Anyone need me to explain again? Anyone need me to explain again? Janet, Raja, Nirupa, Kritiga, Tava, Sajib, Lakshmi. So far, are you okay? You need me to teach you how to derive again? Okay, alright. So this is the Kepler's law. T square is actually equals to KR cube, right? So from Kepler's law is actually from this one, right? T square is actually directly proportional to the cube of the radius. Okay, but you know if you want to change it to the equation, you have to put the constant here, right? So it will become like this. So we already derived, okay? The T square is actually equals to KR cube. Okay, and the next one, right? Derive the relationship between the orbital period of the planet, okay, and the radius of the orbit. Okay, so this one I already teach. Okay, so solving problem using Kepler third law. Okay, this one is actually if they give you two planet, right? Let's say for Earth and Mars. Okay, and they give you the period. Okay, the period and the radius. Okay, let's say they give you the period and the radius for Earth. Okay, and they give you the period of the orbital period for Mars, and they need you to find. Okay, they need you to find the radius of the Mars from the sun. Okay, so this one, okay, from the Kepler's law, okay, so we can compare, right? We can compare, okay. So T2, let's say T1 square, okay, is equals to KR1 cube. Okay, so this is the for the first planet. Okay, and for the second planet, okay, let's say if I have the T2, one is actually 1 and 2 especially to differentiate. There are two planets here. One is for the planet 1, 2 is for the planet 2. Okay, so T2 square over KR2, okay, KR2 cube. Okay, so and then I put like this. Okay, K is actually T1 square over R1 cube. And this one also, I put like this. K is T2 square over R2 cube. So you can see here, the value of K is same, right? So mean I can just equate these two equations. T1 square R1 cube is equals to T2 square R2 cube. Okay, because of the K, the value of K is same for the both equations. So I just can equate this one, right? Okay, and then the next step is, again you cross multiply it. Okay, so T1 square R2 cube is equals to T2 cube over, 2 cube R1 cube, sorry, square. This is square, not cube. Right, this is square. Okay, this is cube. Right. So, and then how you want to to make it like this? So I just put T1, I move the T2 here. This is multiply, right? So when it goes here, it become divide. So T1 square over T2 square. And for this one, I change here. Okay. So it become R1 cube over R2 cube. So I will get the second equation, this one. Okay, this one if they give you two planets, okay, this is for the equation if they give you two planets. And if don't, we just do like, if not, if they can use this one. This is only for one planet. This is they give you two planets and they ask you to find the radius or the period. Okay, so far is it okay? I know it's quite confusing because you got T1, T2 and cube, something like that. Okay. Anything you want to ask so far for this derivation? I get the second equation. Are you okay? The first one is okay for this one, right? I just derive this one and replace with K, right? You already learned this one. And the second equation, are you having problem to understand how does it derive until you get the second equation that T1 over T1 square over T2 square is actually equals to R1 cube over R2 cube. Anything you want to ask, teacher? Okay. So if you are okay, so can you try to answer this question? Okay, for this one, see they give you two planet. Okay, so mean you have to use this one. 2.28 times 10 power of 11. So for this one, you still have to cross multiply also. Only Lashmi got the answer. Anyone else? 2.28. Others? Do you have any problem to get the answer? You want me to teach you how to get the answer? Okay, so let's try. Alright, so the radius of the orbit of the Earth is 1.5 times 10 power of 11. So let's say I put the R1 here is 1.5 times 10 power of 11. Okay, and the mass is 1, and the orbital period of the Earth and the mass is 1 year and 1.88 years respectively. So mean for the Earth here, T1 is 1 year, right? While T2 is 1.88 years. Okay, so this one you need to calculate the radius. So means the R2 here. Okay, so we use the formula here. T1 is 1 over 1.5 times 10 power of 11, right? Can we stop the... I move the background first. Yeah, the answer is 2.2. Okay, so here until here, okay, and then we move to the next one is T2 is 1.88. I need to find the R2. Okay, so this one is actually you have to put a square, right? This one also you have to put square. Okay, this one is cube, this one is cube. Okay, so let's try to calculate. Okay, so this one multiply 1 square is actually equals to 1. So it will be left like this, right? And this one you have to cross multiply on 1.88, sorry, 1.88 square multiplied by 1.5 exponent 11. Okay, close shift here. So you got like this. Okay, and then you have to square it. Okay. So you got 2.28 times 10 power of 11. So that's the answer. Okay, don't forget to square. Okay, 2.28. So the R2 is 2.28 times 10 power of 11. So this is actually the radius, right? So the radius here, it gives you the unit in meter. So you have to put the unit in meter. So make sure you put the formula first, okay? So let's move on to the next question. So for this one, you have to be careful because they give you the height of the satellite. So mean you have to add with the radius of the Earth. Okay, because the radius of the Earth is only from here to here, right? And the satellite is here, but it's already give you this is 380 kilometer. You need to change that one to meter first. Okay, so kilometer change to meter. There are two ways. Whether you just multiply with 1,000, at the other part you can change the prefix, right? You know the prefix of kilo is 10 power of 3. Okay, so you just can replace like that. Is it okay? Long time. Itu jelas apa? Bulat dengan siko?
Ya, okey. Salah
Dia
ni.
tak boleh, dia tak boleh. Jangan letak dekat-dekat.
Saya nak masuk dulu.
Bulat ni. Sorry. 1.52 hours. Right? So others? So means for the satellite to make like full complete circle, okay, it takes like 1.52 hours. Others? Did you get the answer? Or you get like same as we can answer. Others? Sajid? $1.53. Sajid didn't get. Raja? Janet? Nirupa? Oh, Sajid get 1.533. Lakshmi? Tava? Eugene, did you get any answer? Same, 1.533. Okay, so let's see. So we use the formula, same formula, T1 square over T2 square, right? R1Q over R2Q. Okay, so this one, the radius of the orbit of the moon is 3.83. So I just replace R1 with 3.83 times 10 power of 8 and cube, right? And the orbital period of the moon, okay, the orbital period of the moon is 655.2. So this one I take the Earth, right? The radius, sorry, 3.83. I take the radius of the moon. So this one R1, T1 also the orbital period of the moon. So 655.2. Okay. And the question asks you to find the orbital period of the satellite. Okay, so satellite is T2, right? The satellite is T2. Okay, correct. And then the R2 is you need to find. Okay, so this one 3 point radius of Earth 6.37 times 10 power of 6. You have to plus with 380 times 10 power of 3. Okay, so I just change kilo to 10 power of 3. I check again, wait. Okay. This is the moon, T1, and this should be the radius of the moon. Okay, so correct. This is power of 3. Okay, and this is power of 2. Okay, this is also have to power 2. Okay, so now we have to use a calculator. So you have to cross multiply, right? So let me check. Okay. The answer is 1.53. Okay. So let's try to use the calculator. 655.2 655.2 square, okay, and then multiply with 6.37 exponent 6 exponent 6, okay, plus 380 exponent 3. Okay, then you have to cube. Okay, and then you got the answer, and you have to divide by 3.83 exponent 8. Okay, shift cube. Wait, text error. Wait. 2 square times 6.37 exponent 6, okay, plus 380 exponent 3, okay, and then shift cube. Wait, I check again. So many numbers, right? Okay, so I got this one, and then I divide with 3.83 exponent 8. Okay, shift here. Okay, you got the answer. Then you have to square root, right? Square root. Oh, sorry. You have to square the answer here. Yes, so you got 1.53. Okay, so 1.53 hours. Okay, so any question you want to ask teacher about Kepler's law? Anything that you want to hear? So remember, Kepler's law, the first one is the law of orbit. Orbit is in ellipse shape, okay? And the sun is at the focus. Second one is the law of area, the area of the two part, okay? Any two part is same as long the time taken, okay, is also same, right? There is this law of area. The third one is law of period, right? T square, okay? The T square is actually directly proportional to the R cube. Okay, and then we have to derive. We get the formula T square is equals to KR cube, right? So that's the uh, three laws for Kepler's law. Okay, so I think I will stop until here. So the next for the next week on Monday, I will told you I will do the online test. I will give you the Google Meet. Okay, then later we do the online quiz together. And after that, on Tuesday, right, I will continue the last part of the Kepler's of the chapter 3. Okay, I hope we can finish that one. So then we go for the chapter 4 and we discuss about your project. Okay, so what you need to do for your project. So anything you want to ask before I stop the class for today? And I already assigned you two questions for you to answer, two quiz for you to answer in the Google Classroom, so you can answer that on GC. Right, so I hope all of you can answer. Right, so I stop until here. So thank you, class. Okay, take care. Avinash is not here, right? We can. Did you know why?
No, he's not here. He didn't tell why.
I think he's sleeping. I called him twice.
He's sleeping.
Perhaps.
11:30 still sleeping.
Perhaps.
And then after this you have chemistry also, right?
Yeah.
Never mind. I will text. Usually he's not like this, right? Maybe it's no. Okay, it's okay. I will text him. Okay. So thank you, class. Right. Okay. Take care. Have a good day. Bye.
Thank you, teacher.
All right. Bye bye.
Thank you, teacher. Bye, teacher.
Bye.
Thank you, teacher.
Welcome.
Thanks, sir.
Okay. Bye.